Alright, hello. Here we are for part 2 of lesson 6 of CENG 4412 Steel and Concrete Design. So we're going to continue from part 1, which was recorded this morning. And in part 1, we reviewed or we studied the behavior of concrete in terms of increasing, we discussed some of the pros and drawbacks of concrete as a material. And we also discussed its mechanisms for cracking and strength development as you increase an axial load applied to it. But what we really want to get at today is we want to get to one of the most fundamental aspects of concrete design, and that is using concrete or using reinforced concrete to design and construct reinforced concrete beams. Okay, so first of all, I'm just gonna discuss the load combinations, and the load combinations from the ACI code, and of course. In case you're not aware, for concrete design, we're going to be using the ACI, the American Concrete Institute, Building Code requirements for structural concrete, and I'm using the latest edition, ACI 318.14. Now, let's see, in terms of the load combinations, now thankfully for this class at least, the ACI load combinations aren't going to be any different than the load combinations we use for the AISC steel manual. Now, there are many different design codes out there, but thankfully, at least for our standard steel and concrete design codes, they do both reference the ASCE code. So we don't need to reinvent the wheel. There are other design codes. For example, if you're doing, say, perhaps something like pressure vessel design, then there are other codes that you would use for those, etc. So, depending on what exactly it is that you're designing as an engineer. And of course, if you're designing as a structural engineer, you would not want to be designing pressure vessels. That's an entirely different realm of design. You're going to get into big trouble if you do that. But anyway, depending on whatever it is you're designing as an engineer, there's going to be different codes that are applicable to that. And so, as we discussed before in our LRFD philosophy, the load combinations are designed around certain statistical frequencies in mind. So if you suddenly switch to a radically different field of design, then the load combinations that were calibrated to work with, say, regular structures and buildings aren't going to be applicable to whatever it is that you're designing. So if you're designing, say, an offshore oil platform or something like that, you're going to have completely different design loads than you would for a simple onshore structure, a conventional building, that kind of thing. But anyway, for this course at least, we don't have to worry about any of that. We're going to keep things nice and simple and just keep using the design loads from ASCE. And so, for example, these are just the same bog standard, 1.4 dead, 1.2 dead plus 1.6 live, plus 0.5 LR or S or R, etc. All of these from ASCE 710. Or the latest version of ASCE 7. Okay, so then let's look at concrete beams. Now, we realize, of course, that on a concrete beam, it's going to be subject to a whole variety of things. And so let's consider this. Concrete beam design. So let's talk in general first. So if you have a simply supported concrete beam, it's going to need to be designed for a whole bunch of things, or a whole bunch of loads. And there will be a whole bunch of things that your beam will need support, all of them simultaneously, but to different levels depending on load combinations. The first one, of course, is going to be your self-weight. If your beam can't stand up to self-weight, well, it's really not much good for anything. And so you'll have your self-weight on there. You can draw that a bit like this. Oh, that's a little too long. Like this. So we'd have self-weight. Self-weight. Then superimposed upon that, we would have, say, your dead load. Dead load, and then superimposed upon that, you would have live load. But we would simply design for a W that is composed of all of these, and live load. However, of course, we do realize that for a concrete beam, because it's going to be on average have lower strength per unit weight, our self-weight component is going to be a bit more critical for concrete design than it is for steel design. Although, of course, for all beams, you need to consider them. Okay. However, though, we have a couple ways, or we have different ways of approaching this. So, the difficulty with beam design is that, unlike with tension members, now, truth be told, I kind of glossed over this in the tension member unit. We analyze things as true tension members, where you had only tensile load applied. But if you think about if you think about statics, or you think about mechanics of materials, intellectually you can realize that there is no way you can ever have a pure tension member, or at least you can't have a tension member made of anything that has mass, which anything that has weight, etc. Because if you think about a tension member, well, if it's going to actually be made of matter, well, as it's hanging there in the air, it's going to have its own self-weight, and that's going to introduce some sort of bending to it. I guess the one exception would be if you had I guess I should rephrase that. If you had a tension member under a large amount of load, and that load was pure, and the tension member was purely vertical, and the tensile force completely overwhelmed the self-weighted member, well, I guess that would be a pretty pure tensile member, in the sense that at no point along that tension member would you actually have any section in compression or in bending. But in anything other than a purely vertical member where tension absolutely dominates, you're always going to have some amount of, say, bending. Anything at an angle, there's going to be some amount of bending, etc. Okay, but anyway, even ignoring that, when we're designing beams, though, we tend to have a few things we need to consider. So often we're going to have axial load on these beams as well, and we'll worry about that later. But if we're just looking at beams and beams by themselves, not considering any axial loads like compression or tension, we still are going to have what we remember from statics class. And we remember from statics class that every beam is going to be subjected to both moment and shear. Now, in mechanics of materials, when we learn how to do beam design, you just do both of those simultaneously. And in statics, of course, you're just calculating the load, the moments that must be supported. You're not actually calculating you're calculating the shear and moment must be resisted. You're not actually calculating the stresses involved and what kind of sections are required, etc. But for the way concrete works, the way that beams, for the typical loads we carry, bending tends to be more critical than shear. It's very rare for a section's design to be controlled by shear. Now, there are some cases where it does happen, so whenever we're designing a beam, we do have to consider shear, and we have to calculate its shear capacity, but because moment is what tends to control, we tend to design for moment and then merely check for shear. We will design beams for moment and check for shear. And merely check for shear. And check for shear. Again, because that's what usually determines or governs our design, so there's no point, most of your iteration loops, like all design is always occurring in levels of iteration loops where you come up with an initial design, you recalculate your loads based on that, including self-weight, then you go and say, okay, this is either too strong or not strong enough. If it's too strong, if the member is way stronger than you need, and your allowable load is twice as what your actual expected load, your actual factored load is, well, then you might want to lighten the beam or column, whatever it is, up. But then you'll have to readjust things, and your load changes. It's an iterative process. But so that kind of iterative process, that is quite tedious, especially if you're doing by hand. So to minimize the number of iteration loops that we have to do, we tend to iterate based on what is usually the most critical one of our failure modes or design cases. And for beams, at least for concrete beams, what tends to control is moment. So we'll design for moment, come up with a cross section. We'll come up with an initial cross section, then based on that, come up with we'll assume an initial weight, come up with initial loads based on that, design a cross section. And then we will, see how conservative or see if that's adequate or not adequate, and then we can readjust the cross section, then readjust the loads, loop around a couple times until we converge on a until we converge on a value for thickness and reinforcement, etc. And then only once we're satisfied, completely satisfied with our moment design, then and only then will we go back and design and check for shear design or for shear capacity. So again, the guiding principle of our beam design here is that we are going to design based on moment and check based on shear. But I think I might want to run through a brief ultimate load calculation. Now, those of you who've had me for structural analysis, this will be a bit of a review, but for those of you who hadn't or those who don't remember, I think I'll run through a brief example of calculating ultimate load on a beam, and this would apply to steel beams, concrete beams, etc. An example ultimate load calculation for something like a beam, including tributary areas. And this would be for one-way loading rather than two-way loading. Here. Well, let's see. So, now the following information is going to be given in this problem. So consider the following information given. Let us say I have a couple columns, 4 columns, and here between these I have some girders running, and then I have girders running this direction and beams running this direction, and then beams running this direction and girders running this direction. So, and let's say I have 2 other beam lines in between here. And I'll label these as beam A, beam B, beam C, and beam D. And beam D. Then let's say that my length here, let's say I had lengths here of 40 feet, and 8 feet, 8 feet, and 8 feet. So 8 feet between A and B, 8 feet between B and C, and 8 feet between C and D. And let's also say that I have the following lead loads. Wow, I'm just getting tongue-tied. I had the following dead loads and live load. So let's say I am given a dead load of 40 pounds per square foot. Oh, that shouldn't be up there. 40 pounds per square foot. And this would be from decking, floor slab, etc. And then let's also say that I have a live load. So I've often been asked what is the difference between self-weight and dead load. And well, live load is obvious. That's anything that's going to move around in the structure. But dead load can be a variety of things. Sometimes it can actually be permanently installed equipment that is never going to move over the life of the building. And that's not going to generate any kind of vibration, that kind of thing. Live load, but then also, dead load is often considered things like oftentimes dead load is other structural elements. So for example, this particular beam is going to be supporting a chunk of slab, and that chunk of slab would be, when you're designing the slab, I would consider the slab self-weight to be its own, to just be the self-weight. But when then designing the beam that is supporting the slab, that beam, that slab self-weight now becomes the part of the dead load for the beam that's supporting it. So oftentimes dead load comes from other structural elements that you've already designed, because one thing supports another. And this is from slab and decking. Slab and deck. And I'm also told that I have the following section for beam D. So I'm given the basic cross section of beam D. Beam B. Beam B cross section. Here. And the cross sections are like this. So it's going to be a 20-inch deep beam and 14 inches across. So it's a 20 by 14 made of concrete, and I am told this concrete now, as we mentioned previously, concrete's properties are much more variable than steel's, than the properties of steel. Now, obviously, the ultimate strength and yield strength of concrete will vary quite a bit. However, in terms of density, concrete's density, it may vary slightly, but generally it's not going to vary much. And the reason is, if you remember back to our section on, if you remember back to our discussion of steel properties, at the end of the day, 95% plus of all the atoms in steel are iron. Yes, we have, actually probably 96, 97, 98 even are all iron. And so, yes, we add other things to that. We add carbon, and then we add a whole bunch of, and then, we add a whole bunch of other trace elements like molybdenum and chromium and copper and everything else. But really, all of those are just small spices thrown into the iron that will give us various other properties, including higher strength. But at the end of the day, 96, 97% of all that stuff is still iron, and iron has a certain density. So that even though by adding properties and changing the heat treatment, things like that, or by adding different elements and changing the heat treatment and things like that, you can get radically different strengths of steel. At the end of the day, the density is all going to be about the same, about 490 pounds per cubic foot. But concrete, though, because it's made from so many different things, not only different types of cement, but different types of aggregate, different levels of air entrainment, different water-cement ratios, etc., concrete's density or its specific weight are going to vary quite a bit depending on the way the mix is designed. So my default value, if I'm not given any other information, I'll personally assume that it has a density, including reinforcement, of 150 pounds per cubic foot, but often we do have the information handy when we're designing things. And that is the case in this problem. In this particular problem, we are told that our concrete section has a gamma of 125, or a gamma or a specific weight of 125 pounds per cubic foot. Pounds per cubic foot. And then I want to find the ultimate load on this beam. So I want to find the ultimate load on the beam. This is kind of a review again. And I'm going to bake into this some review of tributary areas and at least tributary areas for one-way loading and for load combinations, of course. So find ultimate load, beam ultimate load. And that would be my WU. If you remember from statics, we tend to use W for a... and actually, let me go ahead and expand this. WU and MU, our ultimate shear load, our ultimate moment. But ultimately, the actual load combinations are going to produce our W, our distributed load, our line load. So W is a distributed load, or more in particular, a line load that will be in pounds per foot. Okay, so let's do that. So we've been given all this information, and now we want to use it. So first of all, solution. I need to review a bit of the idea of tributary area. And for dead load, and also we're told here that, let's see, what else do I want to know? And I would also to be told something else, I believe. Let me double check something. Yes, I was also told one other piece of information. And that is that this is supporting a live load here. That I'm told this is also supporting a live load equal to, let's say, 125 pounds per square foot. So we have a gamma, a density of 125 pounds per cubic foot, and then we have a live load of we have a gamma, a specific weight of 125 pounds per cubic foot, and then we have a live load of 125 pounds per square foot. Okay. So let's do that. Solution. Well, I'm just going to go down my list, and what I'm going to try to calculate for each of these is a line load first. And then I'm going to calculate line loads for each of them. Because we are doing beam design, ultimately, I want to get some line loads, some W's. I don't want distributed loads like pounds per square foot. I want a line load, a pound per foot, or a kip per foot, something like that. So first, let's tackle dead load. Well, dead load. Let's see, what else? What do we got here? Well, we're told that the dead load... Oh, actually, no, I already listed that once. I don't need to list that twice. Never mind. Don't need to reinvent the wheel. I missed that there. Sorry about that. Okay, so dead load, we have, now, we have the dead load and the live load. The dead load is 40 pounds per square foot, so that means every square foot of area that this beam is supporting is going to have, that beam B is supporting, is going to support a load of is going to have a load on it. Every square foot is going to have a load of 40 pounds. Now, if you remember tributary areas in terms of one-way loading, if you have two-way loading, you'll have to do a triangular distribution from the corners here, and then you'll have trapezoidal loading on this beam. But for a one-way loading, this beam will basically each beam supports halfway to the next beam. So this beam B is carrying the load is carrying the region that is halfway to beam A and the region that is halfway to beam C. And because now in this particular case, it's symmetric, 4 foot and by 4 foot, 4 foot on one side, 4 foot on the other. So that means that our total width for our dead load is going to be 8 foot. So that means our dead load is going to be 40 pounds per square foot times a width of 8 feet, and that is going to equal then 320 pounds per foot. So we have our dead load. Then we'll have our self-weight, and the self-weight is going to be a little bit tricky. Well, not really that tricky, just more in terms of units going to be a little tricky. Self-weight. So again, I know that the dimensions of this thing are 20 inches by 14 inches, and I also know the density of concrete for this problem, or I keep saying density, if I want to be more proper, I should say specific weight. I know the specific weight for concrete for this problem is going to be 125 pounds per cubic foot. So I'm going to say 125 pounds per cubic foot. Now, and in fact, I might even write it like this, just to help you realize where the units are coming from, or the math is coming from. Some people struggle with this. Then I'm going to multiply by the dimensions, and we can kind of see how this multiplication works just by looking at the dimensions. So the first dimension is going to be 14 over 12. Now the depth of the beam is the width of the beam is 14 inches. Then I'm going to divide by 12 to convert from inches to feet. So that's going to be 14 over 12, and whatever number of feet that comes to. Then I'm going to convert. Then I'm going to have my depth, and I'm also going to convert that to feet. And I'm going to do 20 over 12 feet, and that will come to a certain value, and that's going to be, that's going to be 500 and, that's going to be 243. 243 pounds per foot. However, in our load combinations, we combine dead and self-weight, so our actual total dead is going to be 320 plus 243, and this will come to 563 pounds per foot. So ultimately dead load is just another form of self-weight, although, and that's typically how the ASCE code and AISC and ACI, etc. treat self-weight. Ultimately, it is just a form of dead load. But we can also have dead load from other members, not just the members, the member in consideration's self-weight. Then I'll need live load, and this is going to be calculated really the same way as our first dead load. The self-weight has to be calculated based on member cross-section, but the dead load and live load are just going to be based off of tributary areas and such. And so this is going to be 125 pounds per square foot, our live load, times the tributary area, or tributary width, I should say, of 8 feet. And if I multiply pounds over foot squared times foot, I get a unit in pounds per foot. And this comes to 125 times 8 is 1,000 pounds per foot. And then I want to look at the factored loads. So I have my individual loads, factored loads, etc. Now, we could look at the 1.4 dead, etc., but in this particular case, I can very clearly say that the 1.2 dead plus 1.6 live will control, because the live load is so much greater than the dead load. So then I want to get the factored load. And yes, in a real design problem, or in a real actual structural design application, you would have other loads. You would have, wind load and snow load and rain load and everything else. And so your actual load combinations would be much more involved. This is going to be a simplification for the sake of brevity. And, my videos here, when I say brevity, I mean, if we get something done in 2 hours, we're considering getting done early. So let's keep moving. So the W ultimate, that would be W sub U, that would be my ultimate distributed load, or my ultimate line load. And that's going to be, in this case, 1.2 dead plus 1.6 live. And so that would be then 1.2 times 563 plus 1.6 times 1,000. And that would come to 2,276 pounds per foot. And that is going to be the distributed load that I'm going to design my beam for. And really all of this is leading up to a beam design example in case you can't figure that out. We're going to be, and so we'll be looking at that going forward. Although today I don't think I'm going to work all the way through the beam design example. I just wanted to review a bit how to get your ultimate load for the sake of what we'll look at later. And we'll use this ultimate load in another lecture. Okay, so I would also with that like to actually calculate the ultimate moment. So I've got my ultimate load. So that's going to be my ultimate line load W. In other words, my beam must be able to withstand a factored load of 2,276 pounds or 2.27 kips on every foot of it. So let's look at a free body diagram of this thing. And I'm going to use this to calculate the ultimate moment and the ultimate shear while I'm at it. Free body diagram. So let's just, I'll just consider this as a simple line beam. A basic simply supported beam. Like this. Oh, and this beam is going to be 40 feet long. So we will keep using that. And a lot of this is going to be based on cross-section, so I'm actually going to show a cut that we'll be using as we go through our exploration of beam design. So this is 40 feet long, and the load on here, the ultimate load, we're going to have an ultimate distributed load across the whole thing, uniform load, of 2.276 kips per foot. Now, where things really get interesting is if the load is not uniform. See, for example, you might have live loads that represent, okay, for example, say you had live loads that were applied as point loads and dead loads that were applied as trapezoidal distributed loads. Think about how that would work. Well, the difficulty in that is that you might have to design your section, you might end up with different load cases that will produce different values for shear, moment, etc. And you could, if things were balanced just right, it probably won't happen this way that often. But if things didn't line up, if things were very unfortunate, you could actually end up in a situation where your ultimate moment was controlled by one load case and your ultimate shear was controlled by another load case. And if that happened, things would get very complicated very quickly. But we'll probably avoid anything that complex for this class. We have enough material to cram into this class trying to conclude both steel and concrete design in one semester, which is absolutely crazy, but we'll make do. And so if we did have a distributed load of 2.27 kips per foot all the way along, we would have two point loads of 45.5 kips at either end. And then I'll illustrate the cut that we're going to use. So the cut, and since this is going to be constant and prismatic all the way along, I can just say the cut is really anywhere. I'm going to be drawing a whole bunch of cut sections as we move along. And I'll also illustrate what we would get for shear and moment. And so the shear diagram, and this is a review from statics, well, not really a review, I'm just going to draw the results. Very poor review at best. So again, this is going to be our W. Then we would have our shear, and this would be in kips per foot. And shear would be in kips. And then moment would be in, say, kip feet. Okay, the shear, if you remember from mechanics of materials, or ideally from statics, we would just have a linear shear diagram like this, if I could manage to draw a straight line to save my life. And we would have a value of 45.5 kips here and 45.5 kips here. Then my moment, well, if my shear is linear, my moment is going to be parabolic. And in the case of a very nice simply supported beam, you're going to have a nice parabolic moment curve or moment diagram, and it's just going to be like this, nice and parabolic. And our M ultimate, well, M is I remember for a uniform For a uniform load on a simply supported beam, I remember that the ultimate load is WL squared over 8, and or expressed in the variables we already used, W sub U, so ultimate W times L squared divided by 8, and that will equal a value of 2.276 kips per foot times the length of 40 feet, quantity squared, divided by 8, and that will come to 455 kip feet. And this right here is the kind of ultimate load that we would use to design a concrete beam. So we would also have an ultimate shear, so maybe I could box both of these. This would be my V ultimate, and this would be my M ultimate. So after we do tributary area, after we gather our live load, after we gather our dead load, after we calculate the self-weight, after we convert all of those to line loads and then apply load factors, that is going to be, and also including tributary areas for the live and the dead, that right there is going to be our ultimate design load for moment and for shear. And we're going to design and select a cross-section, or design and select cross-sections to resist this type of load. And we will go into that in the third portion of this video. All right, thank you for watching, and I'll be back.